So the next speaker is already ready. This is Tassilo Witte from CDC GmbH, and he will address recycling of the carbon fibers. And I'm really looking forward to your talk. The audience is all yours.
Yeah, thank you very much for having me here today, giving me a chance to present a little bit about the recycling endeavors we've been doing in the past 5 to 6 years concerning recycling of composites in aviation. Because the crucial task for us at the moment is we have seen recycling technologies pop up since early 2000s, 2005, with 2009, the first recycling company near Stade, Wischhafen, being actually established and fully capable of recycling up to 1,000 tons of CFRP per year. And with what my colleague Isabel Gradat mentioned this morning, 92% of the aircraft being recycled already, one of the major questions is what do we do with the stuff we get out of that recycling process? And in the past, especially for composite CFRP recycling, that has been an issue because the most common way of working with recycled CFRP was get the fibers out of the pyrolysis oven and make some kind of non-woven or injection molding compound from it. But that meant we have a very high-performing original virgin fiber being downcycled into kind of lower performing short fiber used in comparably low-cost applications with low performance. And that doesn't match up for us. So we have a quite expensive recycled product with a comparably low cost, while it had a high performance at some point, very low performance, while it had a high performance before. So that is something we need to tackle. And the idea was basically going along routes a little bit like the cotton industry, because we had been asking ourselves, why do they manage to produce high-quality yarns from a wide variety of natural fibers, natural source, with all the variety that it has, and still manage to produce perfect Egyptian yarns and Egyptian cotton? So wouldn't we be capable of going something along that direction? And this is very interesting for us in many points, because if we have something that has very high performance in the beginning as a virgin material, and then it's being recycled down into something that has basically very, very low performance, it's always a downcycling spiral, and that's not circularity for us. So the best thing we can do is work actually on how to increase the performance of recycled carbon fibers. And the very practical approach there is the best way we can do this is by aligning them, by producing some kind of, we call it either staple fiber yarn or stretched yarn. And this has the additional advantages that it leads to better fiber volume content and a much better usability for us. Because if we try to integrate these materials in an aircraft, we need some kind of performance, because if we don't have the performance of the material, it's going to be heavy. And if it's heavy, we're not going to use it in the aircraft. So that was actually one of the very, very crucial tasks, finding ways of improving the performance above, let's say, the 100 megapascal tensile strength you can get with a non-woven. And we're not the first to think that direction. We are an industrial company, and we are trying to collect and work together with the most, let's say, advantageous partners to bring these technologies forward. And that meant, on the one hand, this is a collaborative project. We have been collaborating with the Fraunhofer IGCV in Augsburg to help us assess different technologies on highly aligned yarns. So this is, in that sense, a collaborative work. And for me, it was especially to get someone who is a little bit more unbiased than me, because I really want those things to work. And they did the proper assessment without any personal bias on that. And what we did was screen the market for who is actually working on that. There are companies like universities like STFE, like the Denkendorf community, V-Carbon, the UK, a couple of companies in the UK and research facilities are working on that area. So we have a bunch of 5, 6, 7 different technologies which in theory enable us to do staple fiber yarn or stretched yarns from short recycled fibers. So we got samples from all those different facilities, different entities, collected them, had them processed at the Fraunhofer EGCV in a hot compression molding process, all as UD plates, and then basically did a couple of iterations of improvement, because they were happy to have us actually assess that properly, because it meant we could give them a little bit of an idea of where the problems are for a practical purpose. In terms of practical purposes, we actually only had two major categories of alignment technologies to assess. The one is carding technology, where we work with a carded non-woven, which is then a little bit oriented through basically a kind of combing process in the carding. And the other one is a version of producing a yarn or a carded veil with a subsequent stretching process for increasing the alignment. But all in all, we always produce a pre-textile, which is basically a slightly aligned carbon fiber textile, either wide width or in a small sliver width. And then we use it either directly or we subsequently do additional stretching. Those are basically the main differences in the materials we have assessed. Practically, this means I have a couple of slides here where I have a lot of data. And I'm not going to read out that all to you, because I want you to take, if that's of interest, I want you to take that home and have this data available to be able to assess this for yourself, to see which one of these technologies work. We always assess the machine direction of production, because basically if you pull a yarn or if you pull a non-woven through such a process, you never get a perfect UD. You always have kind of some fibers lying not in the perfect UD direction, some fibers lying basically 90-degree direction to that. And to use that, the practical approach was pretty simple. We got all these materials. We processed them into flat plates. Alignment manually placed for all of these technologies, since we basically work with very small size coupons and very small batch quantities of material. Then we went back to these companies, most of them, because most of the time we got something, missing a pointer right now, but with the first one or two pictures, you see basically a little bit of a mess of an aligned textile. And that was because those companies or those partners of us weren't aware of what kind of fiber volume contents we are working with, what kind of actually really, really, really good alignment we need. So they sent us their first batch of products, and we processed them and said, that's nice, but actually wouldn't work in that sense for us. And through a couple of iterations with these partners, and maybe you can see it with the images we have here, with the very first iterations of material, it was a non-woven with a slight alignment. It was a mess of a material, and we couldn't actually call it a UD. This was based on the carded wide floor textile, which is just a combed non-woven. And we pretty quickly found that this doesn't work for us. And through some iterations, the most promising technologies that we saw, just by practically looking at it, like what is the quality of the textile you have in front of you, we found that those technologies working with slivers and subsequent alignment actually are much better for us in terms of the quality of the component that we produce. I think might be, for those of you who've seen raw materials or raw processing of AFP tows and any UD textile in aviation, the later images, like tape 3.2 and 3.1, actually look pretty much like an AFP tape that we're used to. And that is and then processed those into composite coupons and did a lot of assessment. And the most important was, do we actually have a good alignment? So is it non-woven with a very slight preferred orientation? This is what you would, I think, these are the polar diagrams, which depict, on one hand, tensile strength on the left side of the slides, tensile strength over orientation of the textile. So with 1.1 and 2.2, you see those are the kind of carded textiles that are just combed nonwovens. And you see basically almost circular shape of this polar diagram, which practically means you have a slight preferred orientation in UD direction, and you have a lot of fibers in other directions. 3.2 is one of those examples where we haven't worked with a carded veil, but with a sliver that had subsequently been stretched. And there you see very, very well what we are used to seeing in UD, with UD textiles. We see a very tight polar diagram along the 0-degree axis, and we see very few fibers in other directions, especially in the 90-degree direction. And that is actually what we are looking for. And just to see if we can confirm that by NDT, so with just non-destructive testing of these materials, we did eddy current testing and physically measured the fiber orientation, just to see if we can match NDT values with the values of when we chemically dissolve these materials and all the testing of the destructive testing. So, just to preempt what all the data on the next couple of slides will be, we did tensile testing of these materials, we did 4-point bending testing, we did compression tests and Sharpie impact tests. So those being, let's say, the most valuable first data points that we can use in such a first assessment of technology. And as I said, I'm going to leave you with all this data. I'm not going to read it all to you, but basically give you the main takeaways. The first, let's say, half of this diagram shows you carded textiles. The second half of the, let's say if we divide it by thirds, like 1.1 to 2.2, the first 5 technologies are carded technologies. Those do have a slight alignment, as we've seen in the polar diagram, but they don't really have the good alignment that we've been looking for. Still, we are looking at performance values way over what we've seen in a nonwoven. So a typical nonwoven would have a tensile strength of 120 at the most megapascal. With even the bad textiles of the oriented carded textiles, we achieved something in the range of 300 megapascal. So 2 to 3-fold increase just by slightly combing those textiles. And by far the best candidate, and those are the ones, all technologies on the right-hand side of this graph are more directed in the subsequent stretching. With some of those, we had adherence issues between textile and the resin. That's the candidate 4.6, where we actually didn't really measure the fiber and the performance of the coupon, but we measured the lack of adherence of resin to the fiber, which is going to be a completely different story in terms of sizing of pyrolyzed and recycled fibers. But you very obviously see one candidate that is standing out far, far beyond the others. And that's one of those technologies where you are producing a carded sliver, basically exactly what the cotton industry does. You're producing thin strand of non-oriented, just slightly bound together fibers. You add a lot of thermoplastic fibers and thermoplastic material to that, which enables you to subsequently do a very, very high degree of stretching to the yarn that you have in front of you. And with that, and this is only the, let's say, 1-year-old data, with that we have achieved, like last summer, around about 900 megapascal on average for these materials. And by now, just add on that, 1050 megapascal has been the average of the most recent trials, developments of these carded yarns. And that actually is a 10-fold increase of the performance compared to what we are used to seeing in nonwovens. And that actually allows us to bring these materials much more into view. And I think, and as I said, I'm not going to read all this. I will leave this data with you, and I'm happy to answer any question about that. But those values are confirmed for tensile strength, they are confirmed for bending strength, they are confirmed for compression strength, and they are confirmed for Sharpie impact properties. So we very, very clearly have a best and most favorite candidate for highly aligned carded textiles or highly aligned staple fiber yarns. And The other, and this, just to maybe clearly point that out, these preferred technologies are based on yarns, high thermoplastic content, and most likely to be used in a thermoplastic application. Because maybe the practical difference between this very high 2.2 and the other ones is that one was embedded in polypropylene, the other one were embedded in thermoset resins. And if you use a polypropylene, a thermoplastic material in general as an adhesion material between the fibers, and you only use a very small amount because you want to integrate it into a thermoset, this means you have very little stretchy stuff between the fibers that you can pull on and do a high alignment. If you already have like 50% of the fibers being thermoplastic, it means you have a lot of wiggle room in terms of how much you can stretch, and the further you can stretch the raw material, the higher the alignment gets, the better the performance gets. So due to the fact that we need some kind of binder between the fibers and the stretching, we are looking at these kind of technology. We are mostly looking at thermoplastic applications if we actually want to do very, very high performance application. And the curious finding was we've been talking a lot about MDCD if you look into the industry. MDCD, machine direction, cross direction, so how much fibers are this direction versus this direction. And we found that this is actually quite a bad measure for this because the machine direction, cross direction gives you a very, very small indication of the performance, but not the real final values. And this is maybe something that we should keep in mind when we brag about highly oriented rCF materials, because they are very different measures. And if I may come to an end with that, because happily answer any detailed question about this later on, highly aligned materials are the way we are going right now. If we want to have a recycled carbon fiber back into the aircraft, it can't be a downcycling spiral. It has to be maintaining the most and the best performance we can recover from these materials. And that is the direction I'm hopefully seeing a lot of companies on the industry taking as well. Because downcycling is nice because it means we are actually working with recycling at all, but coming to circularity needs a little bit of an effort. And with that, just finishing my practical part of this, it also means we are talking a lot about who is doing that, and that's just to give this as a takeaway view and invite you to join us on that route a little bit. We have the VDE student competition who are working in many different areas. One is the medical area, the others are sustainability areas, and that's the people, and those are the guys that will help us solve these issues in the next 20 to 30 years. So I just may invite any company and any student present and listening to join us on that route and join us with these initiatives, because that's just a fun place to be and work it. And with that, thank you very much for your time, and yeah, any question will probably be asked later.
Thank you for your talk. I think this is really an impressive material. The properties you got from recycled carbon fibers, it's really astonishing. We have time for one question. I don't see one. I have a question. Have you calculated the energy saving, because you need energy for the pyrolysis and so on, compared to the new material?
We know very clearly the difference in processing, which is basically very little. The biggest challenge is to get the proper data on what is the impact of the pyrolysis process itself. If you talk about energy values, the current standing would be that a carbon fiber production uses, if you talk cumulative energy values, so KEA or KEV, a carbon fiber, it has an embedded energy of between 220 and 240 megajoules. A recycled carbon fiber per kilogram. A recycled carbon fiber, so stated by the companies who do that, has currently an embedded energy of about 30 to 40 megajoules. So it's bringing it down by quite a large margin, but we have to keep in mind that it's also bringing down the performance because we're cutting the fibers. So it's a little bit of comparing hens and eggs because it's roughly the same thing, but not really. So it's definitely better. It's definitely way better than throwing all that stuff away, as has been done for many times in the past. But it's definitely not the end of the road yet.
So there's still much work to do there. Okay, any further question? There's one. Please use the microphone.
Yeah, hi, Tassilo. Jan Stübe from Delft University of Technology. Did you find in your studies critical fiber length that has to be maintained in the product to reach these results that you have?
It depends on whether you're asking for the academic value of the critical fiber length or the practical processing purposes.
The practical.
Practically, it means yes. If you work below 10 millimeters of fiber length, you get an issue with any kind of stretching because if you have a 10 millimeter fiber on average, you have a 5 millimeter overlap, so you can stretch that material roughly by 50% until you get fiber separation on average. The higher the fiber length is, the higher the degree of stretching can be, but it might impede the prior processing. So carding does not get easier if you have 100 millimeter. So it's kind of, the longer the fiber, the worse the carding, but the longer the fiber, the better the stretching. So it's kind of searching for the optimum in between those two. And if it was a wish, like give me 20 millimeter fibers and I'd be happy.
Okay, so let's thank our speaker again.
Thank you very much for your time. And